Welcome students to our help video on 9-11 Introduction to Stoichiometry Practice Problems Mass-to-Mass Calculations. Some of you have figured out, oh my gosh, this is our second day of doing the same type of calculation. It is. If you figured that out as you work through this, it means you are beginning to see what we're trying to do. Mass-to-mass calculations are one of the most fundamental and important calculations that we do this entire school year. It is fundamental to the subject of chemistry itself. This calculation is chemistry. When we're doing a mass-to-mass calculation, I want to remind you that we are working on the stoichiometry conversion chart. This is the chart we are working off of. Earlier this year, we learned to do the calculations that are pretty much on the left side of the chart and the ones that are on the right side of the chart. In Unit 9, the only thing we learned to do new was the one that it connects these two sides, the one in blue. So we already know for a given substance, if I give you the volume, you can find the moles. There's your conversion factor, 1 mole over 22.4. If I give you moles and ask for volume, you've already learned to do that earlier this year. You multiply by the molar volume, 22.4 over 1 mole. So we can navigate all sides of this chart. The only new one is using the chemical equation. And when we're doing stoichiometry, it just means you're using the proportions on the chemical equation, and you'll be given something about one of the substances in the equation, and you'll ask to find something else or about another substance in the equation. The ones we've been focusing on the last 2 days are what's called mass-to-mass stoichiometry, where you're given the mass of one thing in the chemical equation and you're asked to find the mass of something else. That is a 3-step conversion. You take the mass of what you're given and convert it to moles. You need the periodic table to do that. You'll take the moles of what you're given and convert it to moles of what you're trying to find. To do that, you'll need a balanced chemical equation. And the final step is to take the moles of what you are trying to find and convert it to the mass of what you're trying to find. And you'll use, again, the periodic table. Anytime you go mole to mass or mass to moles, you need the periodic table. Anytime you go mole to mole, you need a balanced chemical equation. 9-11 begins with a problem about looking at the difference between burning ethanol as a fuel and burning gasoline, octane, as a fuel. In this very first problem, what we are doing is trying to find out how many grams of CO2, a pollutant, would be produced by burning 100 grams of ethanol. And we're going to compare that to find out how many grams of CO2 is produced from burning 100 grams of octane. And they're trying to find out which is a little bit more of a pollutant in terms of producing energy for fuel. So ethanol, we were told, is C2H5OH. We were told that right up here. And we have 100 grams of this that we're going to burn. And they want to know how many grams of CO2 we're going to produce. Well, we've got to write a balanced chemical equation. Have to be careful here because this would not be straight Hollister. This is combustion, I agree. But when we use Hollister, it's the combustion of a pure hydrocarbon. This is an alcohol right here. This is an alcohol right here. This has the OH group on it. This has the OH group on it right there. So for that reason, we can have a number that is odd in front of this because we have 2 oxygens here and 1 there. Odd plus even can be odd. So it's permissible to have an odd number. So when we go to balance this one, we realize that we have 5 plus 1 hydrogens. That's 6. 5 here and 1 there is 6. So we can put a 3 times 2 to get 6. And we may be just fine with an odd number in front of that water. We now go to carbon. We have 2 carbons right here, so we put a 2 in front there. 2 times 1 is 2. Carbons are done. Now we check our oxygens. 2 times 2 is 4 plus 3 times 1 is 8. So we have Let me try that again. 2 times 2 is 4, plus 3 times 1 is 7. That's 7 oxygens, not 8. Here I have 1 in this. 7 minus 1 leaves me with 6, so I put a 3 in front. 3 times 2 is 6, plus 1 is 7. 2 times 2 is 4, plus 3 times 1 is 7. We have a balanced equation. And to do a mass-to-mass problem, you must have a balanced equation, because we need that balanced equation to go from moles to moles. We use a balanced equation. So first, we're going to take our 100 grams of our fuel, C2H5O2, or C2H5OH. We have 100 grams, and we have to figure out how many moles that is. That's our first step, converting that mass to moles. So I need the molar mass of C2H5OH. Though our 2 moles, C2 of carbon, 2 times 12O1 is 24O2. We have 6 hydrogens. 5 here, 1 there is 6. 6 times 1008 is 6.048. If you use 1.01 there, you're fine. And we have 1 mole of oxygen. 1 mole of oxygen, 16. 1 times 16, 16. Add those numbers up. We get 46068 as the mass of C2H5OH. Now, how do I know what to put on top? Do I put the grams on top or the moles on top? We look over here, it looks like moles. 1 mole goes on top. So I put the 1 mole on top and the mass on the bottom. If you don't have the chart in front of you, you are given a mass, grams. So grams, C2H5OH is on top. We need it on the bottom so that grams will cancel with grams. And then I'm now in moles. I'm now in moles of C2H5OH, and I need to convert that to moles of CO2. I need the balanced chemical equation. So I put the coefficient in front of the moles of the one I'm trying to find on top. Whatever you're finding goes on top. The coefficient in front of the moles in the chemical equation of the C2H5OH will go on the bottom. So I go up to my chemical equation. It's 1 mole of C2H5OH for every 2 moles of CO2, 1 to 2. I can express that 2 ways. I can put the 1 mole of C2H5OH on top, 2 moles of CO2 on the bottom, or I can put the 2 moles of CO2 on top and the moles of the C2H5OH on the bottom. This is the one I'm going to pick, the one with the one I'm trying to find on top. This side will be on top, 2 moles of CO2 per 1 mole of C2H5OH, just as this tells me right here. What I'm trying to find is on top, what I'm given is on the bottom. If I forget that, I know if I've set this first one up correctly, moles of C2H5OH on top, I need the moles of C2H5OH on the bottom, so that this can cancel, factor out by dimensional analysis. This label should cancel this label. I'm now in moles of CO2. I am now right here on the chart, moles of CO2, and I have to convert that to mass of CO2. To do that, I want the molar mass. I need the mass of the CO2 on top from the periodic table of elements, and moles will be on the bottom. So I need to add up the molar mass of the CO2. There's 1 mole of C in there at 1201. There's 2 moles of O in there at 16 each for 32. 1201 and 32 is 4401. The mass goes on top. The 4401 goes on top. The moles go on the bottom. Why is that? Because this is moles of CO2. I need it to cancel with moles of CO2. I need that label to factor out. We're using dimensional analysis, factor label method. If I get confused on whether grams or moles are on the top, I need grams as my final unit. It needs to be on top. That's what the question's asking. And if I'm still confused, I can look back at my chart. I need grams on top, moles on the bottom. Grams on top, moles on the bottom in my final expression. There's 3 steps. Step 1, step 2, step 3. On my 3rd step, grams needs to be on top. I look back. Grams is on top. In my 2nd step, I need moles of what I'm trying to find on the top, and these come from the coefficients from the balanced chemical equation. What I'm trying to find is CO2. That's my question. That needs to be on top. That's what it says here. I know I'm doing this correctly. The one you are finding needs to be on top. My first expression, I should have moles of what I'm given on top, grams on the bottom. I do. Moles on top, grams on the bottom. That chart's telling me everything is set up correctly. I take 100 divided by 46068, hit equals, times 2 on my calculator, hit equals, times 4401 on my calculator, hit equals. If I burn 100 grams of C2H5OH, if I burn that many moles of ethanol, which is the name for C2H5OH, you would produce 191.1 grams of carbon dioxide. That's our first part of the problem right here. I'm trying to find out which one produces more pollution. So in our second video, we will take a look at how many grams of CO2 would burning 100 grams of octane. Oct means 8, so that formula would be C8H18. We'll take a look at this one in the next video.